Welcome to part 3 of the tutorial on the SAS system for Windows. In this video, we will cover additional data manipulations in the editor window. Once variables are defined using an input statement, you can perform calculations with them. SAS uses the Fortran or basic notations for calculations. The plus sign is addition, minus sign subtraction, forward slash is division, an asterisk is multiplication, 2 asterisks is power, round brackets denote the order of calculation, and SAS has an entire library of functions that can be called. Some of the common ones you may use are the natural log or log to the base e function, the log to the base 10 function, the exponential function, and so forth. For example, perhaps we wanted to convert the 100 seed weight into milligrams instead of grams. To do this, we define a new variable name and indicate the calculation to make. For the weight in milligrams, I'll use the variable name WTMG and indicate using an equal sign what calculation to perform to generate the WTMG variable. So once I had defined the WT100 variable in the input statement, I could then perform calculations with it. So the WTMG variable will be calculated as WT100 times 1,000. So now in addition to 3 columns, the electronic data set called first will contain a 4th column, which will be called WTMG, which will be the values of the 100 seed weights in milligrams. If a calculation can't be performed, such as division by 0, SAS will insert the missing value code for the result. The default code is a single period with no number. SAS will also display this within an analysis whenever a calculation is not possible. Following creation of the dataset first, we could create many other datasets. For instance, you may have a sequence of experiments. Each could be entered as a separate dataset and the series combined within the SAS analysis. We can also begin with an electronic dataset and do further manipulation with it. To illustrate, I'll create a second dataset, which I will call second. Using the set command, I'll begin with the dataset called first. If more than one datasets are listed in a set command, SAS will combine into one large matrix by placing them on top of each other. I can also create additional variables. In this case, I could create the natural log of 100 seed weight. I'll call it LNWT100. The log function in SAS is the natural log. If you want the log to the base 10, you have to call the log10 function. So in this case, I would have created 2 additional variables, one which is the natural log of the 100 seed weight, and the other which is the log to the base 10 of 100 seed weight. I don't need to create a new data set to be able to do these calculations. I could have included it as part of the other calculations that were going on after the input line when I created the first data set. But here I was just placing it here for illustration purposes. We can also parse a data set. For example, perhaps I only wanted to analyze the sunflower values. I could remove the values for corn from the dataset using an if statement. So now I have 2 datasets. The original one with all my values, and that's I've called first, and the second one, which now only has the values for sunflower. Note that the command lines are not case sensitive. I can use, so both of these statements would be treated exactly the same. The only situation where case sensitivity is important is when you have values for an alphanumeric variable. So consider 3 possible ways of typing corn. CORN all lowercase, CORN all uppercase, and a capital C ORN. For an alphanumeric variable value, SAS would treat these as 3 different values for the species variable. They would not be considered the same. So if you're dealing with alphanumeric variables, make sure you don't have case alterations going on in the data sets. And sometimes these appear when you're bringing data sets in from different sources. In a spreadsheet, go in, block the data region, and convert the case to be all upper or all lower, and that way you don't have case issues going on within your data set. Such case changes often occur when you're bringing in data from other researchers, or more typically that I've seen, if you're dealing with data from different years. You can also do other types of if calculations. For example, here's one. So this if statement would eliminate from the data set all replications greater than 5. I'll remove these illustration statements. In some analyses, you may need to combine data from the same experimental units. For example, if you had sent samples to another lab and they recorded the percent protein and calcium in each sample, you don't have to spend time trying to merge the data in a spreadsheet. So long as there is one unique variable in common, perhaps a plot number or sample code, then you can have SAS merge the value for you. Read in each of the data sets as separate data sets and use the merge command to bring them together. So in this example set of code, I've had two data sets, one called mine, one called lab, and there is a common variable in each called sample ID. And so what this will do is take the two data sets, merge them, and using sample ID as the common value, and it would then be able to take each sample and align the values for the two sets of data and bring them together as one larger one. So that's another powerful tool that the SAS program provides for bringing data together. So I've now returned to my earlier example where I'm creating this data set called second, beginning with the first data set and calculating two additional variables, the natural log of the 100 seed weight and the log of the base 10 of 100 seed weight. And to ensure SAS completes the series of steps before going further, we need to insert a run statement. And always remember to finish lines with a semicolon. If you're changing a title, you would require a run statement before the change in title. If you're doing a complex series of analyses, by inserting a run statement after each phase, this ensures that SAS completes the task before starting the next. The SAS software is designed to optimize usage of the computer time, and so in complex analysis, it may proceed to later steps, perform some of those, while it is waiting for an earlier computation to finish. And if you don't force it to complete sections using the run statement, you may find results of a later step intertwined within the results of an earlier step. This concludes part 3 of the tutorial. In part 4, we will cover some basic procedures and how to capture results of an analysis.